there, students, and it is time to talk about multiple regression. This should be the last lecture of Module 6 in our class. And to understand what we mean by multiple regression, it'll be important to take another look at what we've been doing so far. I mean, we've been making these regression models, like this first one I have up here at the top, where we are doing a statistical model to estimate a random variable. This is going to be y hat. That's our estimate of the real random variable y. And we have some regression parameters, some regression statistics, that is, like b0 and b1. And so our simple linear regression model is just that b0 is equal, let's put it this way. Y hat is equal to b0 plus b1 times x, where x is our independent variable. Now, we had other slightly fancier models where we were doing second order regression, like we were saying that there was both an x and an x squared term, so that we could maybe, instead of be fitting a line, be fitting a parabola or something to our data. Now remember, that b0 and that b1 and that b2, they are different values than what you had back there in the first regression model. That b0 is not the same as the other b0. It's just another constant that comes from when you have that nonlinear term. Now, we're going to have then another possibility here where we're going to start having a new type of regression model, a new kind of statistical model. Again, y is being estimated, y hat, by a function of some regression statistics like b0 and b1 and now b2. But notice now we actually have two independent variables. See, in the first version of the regression equations that we've had so far, these statistical models, we had one independent variable, x. It had many observations of it. So like if we were trying to estimate the amount of power being produced by a wind turbine, and we were estimating it based on the wind speed, okay, wind speed was our independent variable for predicting our dependent variable, the power produced by the wind turbine. But there was just the one independent variable, wind speed. Now we have multiple independent variables, x1 and x2, each of which has multiple observations in it. So x1 would be maybe the wind at the station, and there's lots of different observations of the wind speed. And maybe x2 is some other parameter that might describe the maybe the efficiency of the windmill, of the turbine, or maybe if you have some reason to think that the temperature is a factor because it changes the density of the air or something like that. Then that would be your second factor there. You, instead of having ordered pairs though of data, x and y, you now have ordered triples, where you have two different independent variables and one dependent variable. Just to give you an example of the kind of problem you could be addressing with this, maybe you had some reason to think that the power output from your wind turbine depended on both wind speed and how long it had been since the turbine had routine maintenance. Okay, that would be an example of two different independent variables that together might be able to produce a forecast of a dependent variable, like the amount of power that the wind turbine is producing. So our first random variable we'll call x1, in this case maybe it'll be the wind speed, and our second random variable we'll call x2, maybe that is, you know, how long it's been since the turbine has been serviced or something like that. And those two variables together, we want to create a statistical model that can be used then to forecast y, which is our dependent variable. So again, just to be clear how I label that here, the independent variables, the things we're not in control of in our experiment here, are the wind speed and how long it's been since we've had service, whereas the dependent variable, what we're trying to make estimates of in this case, is power output from the wind turbine. Now when you take a look at that equation here, that equation is not the equation of a line. If you think back to your geometry classes or algebra classes or something like that, that's actually the equation of a plane. And this can be very hard to picture. We're not going to produce like three-dimensional scatter plots or anything like that in this class. It just gets too messy. But this is the equation of we are fitting a plane to the data rather than a line to the data, where we have two independent variables. One is like on an x1 axis and the other is like on an x2 axis. And based on every observation of x1 and x2, there is some dependent variable. We're trying to fit a plane into this cloud of dependent variables. Again, it gets to be really hard to visualize this, and it certainly gets impossible to draw visualizations of this once you get into higher. I mean, we could have had 3 independent variables, we could have had 4 independent variables, we could have had n independent variables. So the idea of actually taking time to learn how to render these planes in Octave didn't seem like a very useful thing, considering if the regression model had gotten any more complicated, we would have not been able to visualize it with our puny human minds anyway, because we can't think in 4 dimensions or 5 dimensions or whatever. Now the question I want to figure out is, how are we going to actually get this B0, B1, and B2 so I can actually make a statistical model based on some independent variables, how to predict our dependent variable? Well, there's going to be a nifty function that we're going to work with, and it's going to be called regress. Now, you might remember when we did linear regression, we used polyfit as our function. In fact, polyfit is equivalent to using regress when you only have one independent variable, but we'll get there. Regress is actually the better one to use, the better function that's built into Octave to use when you have multiple regression, when you have multiple independent variables. Now, what I'm going to do here is I'm just going to show you some screen captures of what a little program I did. Rather than mess around with the OPPD data or the wind power data, let's just go back to the Nebraska temperature database that we worked with before, and I'm going to take just 3 stations in January. They happen to all 3 have, none of these have any missing data, so it kind of simplifies things a little bit for us here. I happen to save Howells, Ord, and Falls City. Again, if you look through your program here, you can see exactly how this is being done. I extracted just the Januaries, and then for each of those 3 stations, I just extracted them. The advantage of those 3 is that they never missed an observation. And so I don't have to worry about the business of filtering for that or whatever. Now look at what I actually ended up doing here. Just to be clear about it, I put the data from Howells, the maximum temperature data from Howells, into the Y variable. I'm going to make Howells be, the maximum temperature in Howells is going to be my dependent variable. I'm trying to make forecasts of the temperature in Howells as a function of the temperature in Ord and Falls City. Okay? Not that I have any reason to think that there should be any, but whatever. I mean, this is our statistical model here. Can we predict the high temperature in Howells if we know the high temperature in Ord and Falls City? Alright, so I've just moved column 5, which is the maximum temperature from the data Howells directory, from the data Howells array into Y. Y will now have, well, there's 10 years of data times 31 days per month. That's 310 values in that variable Y. Just a column of data there, if you can picture like a spreadsheet or something like that. Then, we need to create an array that's going to hold the independent variables. Notice plural, independent variables. It's going to have as many rows as there are in the Y array, but it's going to have columns for each of the independent variables. Now, there are better ways and worse ways to do this, but the sneaky trick that I think is probably the best is to use a neat little trick that is built into Octave called ones, O-N-E-S. What I'm going to be doing here is I'm creating a new array. I'm calling it big X. Why am I calling it big X? I'm using big X to mean that this is the array holding lots of independent variables. It has columns, 1 for each independent variable. Why am I doing it that way? Actually, when I read the documentation for Octave, that's how they did it in their examples. They used big X as their array, so that's what we're doing too. Now, what this ones command does is it creates an array with some number of rows and columns and just goes ahead in advance and fills in the number 1 in all of those spots. There is a similar function called zeros that will that creates an array with that many rows and that many columns, but just puts zeros in it. Whatever. I mean, it's handy in this particular case, as you'll see. So what we're going to do here is we're going to create a new array called X, and it's going to have the same number of rows as there are in Y. So my first argument to ones, which should be how many rows I want the same number of rows that are in Y. So I'm going to use that rows function that we found so handy a couple times now in this course. Alright, now the number of columns in this new big X array needs to be how many independent variables there are plus 1. So like in this case, because we're going to be building a regression model with a statistical model with 2 independent variables, temperature in Ord and temperature in Falls City, that I need 3 columns. The reason why we're going to do that will come clear in just a minute. Once we've actually created this array that's full of ones, 3 columns of ones with 310 rows of them in there. Look what I do here. I'm going to take my X, all rows, column 2 is going to become my data from Ord. my data from ORD column 5. All those values that were from ORD, just stuff them in column 5, which was maximum temperature, put it in column 2 of my X array. Do the same thing for column 3. Go over there and just move all the values over from Falls Cities column 5, the maximum temperature, into all rows column 3 of X. So notice what that means. I haven't changed the first column, all rows comma column 1 of that X-ray, so it's going to still be 1s. Weirdly, you have to have that. The regress function expects the first column of that independent variable array to be 1s. And then the second column to be one of your independent variables, and your third column to be another one of your independent variables, all the way up to however many independent variables you are. But the first column has to be 1s. Why is that? There is a technique that you might want to use in certain applications where you wouldn't have that 1s there. We aren't doing that, but you normally wouldn't. But because there might be applications where you don't want to do that, Octave built that in that way. They said you're going to need to have that. If you mean just regular multiple regression, just making sure that your first column in your array of independent variables is all just 1s. All right, if them's the rules, them's the rules. All right, so we got this figured out. So if you take a look here, I actually used display to just take a look at what this big X array looks like. And you can see how the first column is just a bunch of 1s. And then the second column is a bunch of maximum temperatures in January. I believe that's in ORD. And then the second column is a whole bunch of maximum temperatures in, the third column rather, is a bunch of maximum temperatures in Falls City. Okay, and it goes down, I only am showing you the first screen full of it, but I mean it goes down 300 and some odd rows. Fantastic. Now it's time to use the regress command. And if you forget this next part, you're going to get an error. But the error will tell you what to do. It'll tell you that regress is not turned on by default in Octave. You need to type this command, pkg load statistics. Statistics, a lot of the fancier statistics tools don't load automatically when you start Octave, just because they're not that commonly used. And so your Octave command, your Octave program rather, like I'm writing right here, you have to actually have a line that says pkg load statistics. There are hundreds of these packages of more specialized tools in Octave, specialized tools for electrical engineers, specialized tools for medicine, specialized tools for any number of different techniques, and it just doesn't make sense. It would take forever for Octave to load if they had to load everything. So because we're using one of the fancier statistics tools, we have to actually load the set of tools that includes regress. Alright, so make sure you include this pkg load statistics, but if you forget it, the error message is explicitly, it looks like you haven't turned on the statistics package, add the following line to your program, pkg load statistics. Okay, we can do that. Now it's time to execute that regress function to perform the multiple regression. So I have a little line there. I decided to call my output beta. Okay, because I mean, you know, beta, B0, B1, B2 are the statistics. If it was talking about parameters, it'd be beta naught, beta 1, whatever. I call it beta when I made this program. Notice, though, there's something really strange about regress. It's y, comma, x. Everything else we've done in this class, when we've worked with a statistics function, you put the x data, comma, the y data. That's how Cora worked. That's how polyfit worked. Well, guess what? For whatever dumb reason, regress works the other way. The y data goes first, comma, the x data comes afterward, where x is that big array that contains multiple columns with one independent variable in all of them, except that first row, which is actually just a whole bunch of 1s. I'm sorry, that first column, rather, which is just a bunch of 1s. All right. Why Y then X? I don't know. And when I talked to the teacher who used to teach this class, he said the students always hate this. They get polyfit where it's XY and regress where it's YX, confused. There actually is a computer science reason why they do it this way, but that's beyond the scope of this class. Suffice it to say, just make yourself a sticky note and slap it on your computer or something like that to remember when you use regress, it's Y, comma X, not X, comma Y. Okay, so the result will be this, in this case, in a little array called beta. That will have, in this case, because it's just got two independent variables, it'll have 3 numbers in it, B1, B2, and B3. So if I actually went ahead and just, like, after running this program, displayed beta, I get the first number is B0, then the second one is B1, and the third is B2. All right, well, that's pretty slick. And then I could do things like make a regression model where I could, you know, estimate the value of temperature in howls as a function of the temperatures in Ord and what was the other one? Falls City. And, you know, for whatever reason you want to do that, a more likely thing that you're going to be doing in like Project 3 is to be forecasting the electrical load in Omaha as a function of things like temperature and wind in the city, or temperature and day of the week, or something like that. So, I mean, these kind of multiple regression models are a powerful tool. Now, because you're getting these statistics, B1, B0, B1, you can actually, there are tests out there that can help you determine if those values are statistically significant. If your value of B1 and B2 are close enough to 0, well then the value of X1 or X2, depending on which one, you know, like let's just say B2. If B2 is close enough to 0, well then it doesn't really matter what what X2 is doing, because you're just multiplying it by a number pretty darn close to 0. Okay? There are statistical tests to help you determine, are B1 and B2 statistically significant? Do I even need to include this second independent variable? For that matter, tests exist that determine whether the multiple regression model that you're creating is parsimonious. Or would you have just been better off not making a multiple regression in the first place and just using a linear regression? I mean, does including our second factor, like let's say we were on that example of Howells, Ord, and Falls City. Making a forecast of the temperature in Howells as a function of Ord is simpler than making a model of Howells as a function of Ord and Falls City. If it turns out that you don't actually gain very much, the correlation isn't that much better, the slope of these planes aren't that much better when you add the second city, there are in fact tests to determine your model would be more parsimonious, it would exhibit parsimony, if you got rid of Falls City and just forecasted Howells as a function of Ord. Those tests exist. If in your future career someday you need that, you will remember, because poor Dr. Schrage tried to teach about that kind of stuff a long time ago, and you can look them up. Okay, they'll be in your book. Okay, we're not going to actually do that for, say, Project 3. We're going to just go ahead and compute all these regression models. We're not going to worry about their statistical significance of their slope or the parsimony of the tests. That's stuff a stats major loves. It's not necessarily what we're doing right now in this energy course. Now in Project 3, you're going to use multiple regression as a way to forecast electrical load in Omaha as a function of various meteorological parameters. I think you're going to find Project 3 really interesting. Now I think this is the end then of Module 6, and you're ready to go into Project 3 and see what you can do. Alright, please let me know if you have any questions. This has been Dr. John Schrage.